Good afternoon, everyone, again. I think I introduced myself, so I won't again. Just my name, again, Spiros. On the first part of the presentation, of my presentation, we focused one aspect of the AI-powered engineering toolset that we have, Physics AI, which is mostly related to the component level analysis of products, and now we're going to see how you can leverage our technology to build what we call digital twins using artificial intelligence, basically. So I'm showing again the same slide just to sync up, and in our first presentation we focused on the right hand side. Now I moved it, the new one, to the left. So now we are going to talk about the system level analysis. And what do we mean about when we call digital twins? A lot of people mean different things, but basically we want to have as much information about our system modeled inside, virtually inside our CAE toolset. And for this reason, we of course need to combine a lot of physics together and a lot of models together. And what happens most of the times is that there's a bottleneck, right? So you have multiple systems working together, and one system, for example, here we have an HVAC unit. The CFD simulation of the passenger, in this case a passenger vehicle, is the bottleneck, because you all know that CFD simulations are a lot slower than, for example, HVAC simulations, right? So what we'll see today is how you can leverage artificial intelligence in order to be able to integrate all of these disciplines together and do it as efficiently as possible. So this is an analogy in what we're trying to do with artificial intelligence here. So we basically, let's say our system is the guitar with the strings. This is what you want to design as an engineer. But in order to properly design it, you need to tune it first. So you need to find a way to be able to understand how to tune these equations, or how to tune the strings here, in order to describe your system, so your guitar. This is where Altair comes in. So we have built, let's say, the tuner, which automatically, as you play, is going to identify, let's say, what is the response of your system, and is going to allow you to tune properly your system. So this is what our portfolio aims to do. Just to give it to you in a graphical sense. So more into the actual software. For this purpose, we have developed ROM AI, which is, ROM AI stands for Reduced Order Modeling, ROM, and AI stands for Artificial Intelligence. So how is ROM AI different than the competition? Traditional machine learning models are treating, let's say, the data in a dummy way, let me put it this way. So they are trying to estimate the time series of data. ROM AI, on the other hand, is a unique combination that is leveraging dynamic system theory with deep learning. So basically, dynamic system equations, classical differential equations with machine learning, with some deep learning networks. And this is, when we combine these two, we have ROM AI, which is basically a formulation which allows you to model both static and dynamic systems. And all is required from the user is a data set in a CSV format. So you can understand that it can work with data from any tool. The CSV is and export just some text. And also, apart from the dataset that is required, we need to, the user needs to specify some parameters. So the main parameters are what does my system look like? So what are my inputs? What I want my system to have as inputs? What I want to predict, what are the outputs? And what is the state vector? Now, I will go a little bit into detail in later slides about the state vector, but state means memory, because when we want to have dynamic systems, we need to also include some memory effect in our model. And memory meaning that the next time step that I want to predict has some memory from the previous time step. So that's why we have here the state vector. But we'll see that more in detail with some practical examples. So, what is ROM AI? ROM AI is a no-code application, right? We have developed, like physics AI, it was developed by engineers, for engineers. So there is absolutely no scripting required. You don't write any line of code. It can be used with both simulation or field data. So around 50% of our customers use it with data coming from measurements, so from actual data acquisition systems. And it can work both ways. You can build static or dynamic systems. Now, what does static mean? It means that for a given input, I have one single output. Dynamic means that for a given input, I might have a transient response, I might have an oscillation, and I don't just want the final value, I want to see also how this time evolution, how this oscillation is going to look like. Now, one of the main benefits of ROM AI, apart from being a no-code application, is the deployment. It's very flexible in terms of the deployment, meaning that it can be deployed on hardware and on the cloud, apart from your actual PC, your laptop. That means that it can run into embedded systems, so you have microcontrollers. If you have a device on the edge, if you have something that is going to be run remotely, or if you would like to connect it via an IoT system to also read from your fleet outside of your working range. And it's very light. Apart from the easiness of the deployment, it's more than real-time compliant. So it can run in pretty much any hardware in real time. All right, so a little bit about the terminology, just to clear things up. We have two names. One is reduced order model, and one is system identification. Which is what? When we deal with results coming from simulation, so when we have a 3D solver, a CA solver, or a thermal solver, and we want to create a faster model out of our existing data, we call this a reduced order model. On the other hand, when we have actual real-world data, so measurements, we call the process of identifying the system identification. In both scenarios, in both the left and the right scenarios, the mathematics to find, let's say, and use ROM AI are exactly the same. It's just a terminology and a matter of explaining things. So we can do both. You can train a model using both, and if you are, let's say, able to do it on the left-hand side, you can do it on the right-hand side. You don't need to follow a different training, let's say. So I'm jumping into some practical examples here, just to make you understand what this solution can do. So here we have some very common crash analysis. This is done, by the way, with radios, our explicit solver, our explicit crash solver. And this is a demo that we did for a conference a couple of months ago. So it's a small, relatively small model, but actually shows the value of this. And basically, in these scenarios, you have multiple design variables. In this case, we were changing, I believe, 5 different design variables from ranging from material thickness, material yield strength, and some dimensions of the actual structure. And we want to build a model out of the radius simulation, out of the crash results here. These are radius results, high fidelity simulations. We want to build a reduced order model that is going to run in real time. Why? Because when we have this reduced order model, we can run an optimization. And why do we want to run an optimization? Because we want to find the optimal combination between all of the parameters. All right. So this is what typically results from ROM AI look like. You can notice here that, for example, the global intrusion is lined up line on line. Also the internal energy and some force results. However, if you take a look at, let's say, the acceleration, you can estimate, you can understand that we do not capture the noise. A reduced order model is not capturing, let's say, noise from data. So if you want, it kind of smoothens also the results for you. It's a built-in effect. Now, arguably, someone might say, okay, this is not noise, this is a part of the crash procedure, but basically, think of it like if there is no relationship between your input and the output, there is no way that any AI model can capture it. In this case, it was purely noise from the data. All right. One of my favorite, let's say, categories into which ROM AI can be useful is actually building virtual sensors. So what is a virtual sensor? Imagine that you have, in this case, you have a multi-plate clutch system, and you have some internal components of the clutch system that you know are failing, right? They are the most prone to failure. The problem is that you cannot instrument these internal points inside the complex system, inside rotating assemblies in general. So what can you do in order to monitor things there and make sure that everything is under control? One thing is that you can run simulations, right? You can run 3D simulations, thermal, and create a model and actually see what's happening inside there. The problem is that these simulations, because of the nature of thermal and maybe CFD and maybe there are some structural interactions as well, these simulations takes a lot of time. Like, you cannot have this simulation run in parallel with the actual vehicle running. It's impossible. So what do? You run the simulations offline on whenever you want, locally or on some cluster, and then you build out of these simulations a model. We call it reduced order model with ROM AI, which runs real time, and it encapsulates basically all the information that is needed from the 3D models. So this model, because it's reduced, it's fast, can now run inside hardware. So it can run on parallel with the actual vehicle. So you leverage the info that you have from the high fidelity simulations and deploy them into the actual vehicle or into the actual airplane, whatever system you have in use. And this is very powerful, and it started to be used quite heavily in the automotive industry because it allows you to monitor things that are unseen. You cannot see them. You cannot place a sensor inside a gearbox in certain locations. Of course, in order for this to work, you need to have some sensors inside the vehicle. So you might have some sensor placed on the housing. You might have some sensors from the canvas of the vehicle. You will use this, but the key point here is that you want to estimate something unknown. So that's where this virtual sensor comes into place. Why ROM AI is good here? Because the model that we are building is dynamic. So when we talk about temperatures, imagine that if I just give you some inputs, some random numbers, you cannot just tell me what's the temperature at a specific location. The temperature there depends on the whole time evolution, the whole time history, what happened on the vehicle as it was riding. So that's why we need dynamic models. And this is where ROM AI is very powerful at. This is an example. I like this very much because it actually won the award in the Excellence AI application in a recent conference. We have also a testimonial here from the chair engineer explaining how he did things into detail. It's around a 20-minute presentation. For anyone interested, you can check it out in our website. I'm just going to go very briefly into it. Imagine that Chery wanted to optimize the controller of their HVAC system built into vehicles, basically to improve the passenger comfort. To do that, they were using Simulink, right? MathWorks. And they were also using Cooley, which is Gamma Technologies, outside of Altair, both products. The problem is that in order to do the optimization, they had to wait for the Cooley simulations to converge every time. And this was very, very time consuming. So what they did is they basically created a ROM AI model based on the Cooley simulations, the 1D Cooley simulations, and then they ran the co-simulation between the Simulink and the ROM AI model. So basically this is the 1D Cooley model, and this is the ROM AI equivalent, the predictions, let's say the R-squared. And you can see here that the whole time history evolution is pretty much line on line with the new co-simulation. It's a very nice application. It shows that I like this a lot because it shows that we can work with results from other vendors as well. We don't require you to use Altair tools only. Of course, we like you to, but in case you have already an existing workflow, you can use the data, train a model with ROM AI, and then integrate it wherever you want. This is, let's say, a public example that we created because something similar to that was done by Mitsubishi. I think I presented to you the Mitsubishi case last year in Prague, so I didn't want to present again the same one, but I wanted to present the public one that we did. And it's still on the HVAC side, but it's a little bit different here. Here we use the ROM AI model in order to predict the temperatures inside the cabin. So basically based on some inlet flow rates and inlet flow temperatures, we build a reduced order model that is predicting the temperatures on the key locations here. And why is this powerful? Because basically, just by running 3 different simulations here, we can estimate scenarios that are well outside our training range. So our training range are these 3 blue lines here, where the x-axis is the velocity and the y-axis is the inlet temperature. And we will test it in well outside the range to see if our training model is able to generalize well. And actually we see that this is, let's say, our training data. And when I test it, we can see that the comparison between the blue lines and the green lines, with blue is ROM AI, green is the actual dataset, are pretty much line on line. So we can be confident that this model can work very well outside of the training range in any case that it might encounter. Now, why would we do that? Again, we want to build a controller here for the HVAC. So you might see here that we have some reference temperature that we want to set, a set point. And we can change, for example, here we will play with the controller. In this case, it's a simple PID controller just to showcase things. But we can see that, for example, if we change the integral gain and run again the simulation, now the temperatures will be much better and will reach the steady state in seconds. If we had the 3D CFD model, we would have to get this result, we would have to wait for 12 hours minimum. We just clicked run and we got the same results that we would have from the actual 3D simulation. That's the power here. So, to close things off, just in time, what is our differentiation here? Our differentiation is that I have several discussions in the break, and I can understand that it can be in the beginning a little bit confusing into which tool I should use for each application. The good thing is that we have all of the tools available. So whatever the application is, we will probably, if it's inside the mathematics, and let's say if it's feasible, because we cannot do magic. You cannot predict something that you have not completely seen, right? AI is not some kind of magic, or it's purely mathematics. It's basically a smart way to reuse your data. But the good thing is that we can cover pretty much any engineering application. We've worked with lots of applications. We have built the expertise. So I highly encourage you, feel free to contact me, Advanced Engineering, whenever you feel more comfortable with, to discuss into future calls what is your, let's say, struggles, your everyday struggles, where are your challenges, so we can see, okay, maybe AI can help you here, or maybe a different solver from ours can be helpful here. We don't just want to sell AI whenever we want. We want to sell it where it's actually useful. All right. That's it from me. I'm open for questions, or if you want, I think we have a break, so we can even ask me questions afterwards. Thanks a lot for listening.